Hello, today we are going to go over the ratio test for series. What does the ratio test look like? Well, when we perform the ratio test on an infinite series a sub n, we take the limit as n approaches infinity of the absolute value of the ratio between the a sub n plus 1 term and the a sub n term. Evaluating this will give us a value for the limit, which we will refer to as L. So what does a ratio test tell us? It gives us information about how a series behaves as it goes to infinity. We study the behavior of the series by comparing the ratio of the nth term and the n plus 1 term and observing how this ratio changes as n approaches infinity. Using this test, we can describe the behavior one of two ways: absolute convergence or divergence. However, there may be cases where the ratio test gives us an inconclusive result. An inconclusive result means that a different type of series test will need to be performed to determine the convergence or divergence of the series. Now, why do we want to use the ratio test? Why not a different test? The ratio test does not require us to compare our series to another series like the limit comparison or direct comparison tests. It is also helpful for series of particular forms, like series with factorials. As mentioned before, a ratio test can lead us to three different conclusions about the behavior of the infinite series. Once we perform the ratio test, we are left with the value L. Remember that L is the value of the limit as n approaches infinity of the absolute value of the ratio between the a sub n plus 1 term and the a sub n term of the series. If this value is less than 1, then we can determine that our series will converge absolutely. If this value is greater than 1, then we can determine that the series will diverge. Our last conclusion occurs if L is 1. In this case, the ratio test is inconclusive, and a different type of series test will need to be performed to receive a conclusive result about the series behavior. Let's practice. The example we are going to work on is the series represented by the sum from n equals 1 to infinity of n minus 2 divided by the factorial of n plus 1. To begin with, let us find the pieces of the formula for the ratio test. The a sub n term is given to us, and we can find the a sub n plus 1 term by inserting or substituting n plus 1 where there are n's in our a sub n term. We will then write these pieces as a ratio. For this example, this gives us the limit as n approaches infinity of the absolute value of the ratio of n plus 1 minus 2 divided by the factorial of n plus 1 plus 1 and n plus 1. And for the denominator, we have n minus 2 divided by the factorial of n plus 1. We can rewrite this ratio as the product of the numerator times the reciprocal of the denominator. Simplifying our fractions, we are left with the limit of the absolute value of the product of n minus 1 divided by n plus 2 factorial times n plus 1 factorial divided by n minus 2. From here, we can continue simplifying the inside of the absolute value. Since the factorial is the product of terms from 1 to its argument, we know that the factorial of n plus 2 is the same as n plus 2 times the factorial of n plus 1. This leaves us with an opportunity to simplify our equation since there is the factorial n plus 1 in both the numerator and the denominator. This leaves us with the following limit. With further simplification, we can have a limit as follows. We know that as n approaches infinity, our numerator will always be positive in the case of n minus 1. And since the denominator is squared with n squared minus 4, it will also always be positive as n approaches infinity. This means that we can drop the absolute value symbols. This leaves us with the step of solving the limit to get our L value to determine the convergence of the infinite series. For this limit, we can apply the horizontal asymptote rule because it is a limit where n approaches infinity and is a ratio of polynomials. I have written this rule to the side to remind you of what it is. For this limit, the leading term in the numerator has a smaller power than the denominator. This means that our limit will evaluate to 0 as n approaches infinity. Thus, for this example, because the limit evaluates to 0 and 0 is less than 1, we know by the ratio test that the series will absolutely converge. Now let's review what we learned. To perform a ratio test, we will take the limit as n approaches infinity of the absolute value of the a sub n plus 1 term divided by the a sub n term. Evaluating this limit will give us the value L. From this L value, we can determine the behavior of the infinite series. If L is less than 1, then the series will be absolutely convergent. If L is greater than 1, then the series will diverge. If L is equal to 1, then the ratio test is inconclusive and a different test will need to be performed. If you are looking for more resources to learn about the ratio test for infinite series or other series tests, feel free to look at any of the links here. Thank you.